Андрей Егоров, про оценки будет лучше на экране. Пожалуйста.
На русском, лучше на английском.
Ну, наверное, на русском будет.
Значит, по-русски, да?
Давайте в конце эфира.
Давайте, да? Okay. Thank you. The topic of my talk is volume estimates. Volume estimates for hyperbolic polyhedra. I'll start by formulating the following conjecture, which is called the maximum volume conjecture. It's analogous to known volume conjecture. So imagine you have a gamma, which is a G-connected plane graph, and then the following equality holds. So on the left side we have, they construct some sequence of invariants called drive-through invariants for graphs, and they consider this limit. And on the right side, we have a supremum of volumes of polyhedra P, where P is a generalized hyperbolic polyhedra for which gamma is the one skeleton. So we consider supremum of volumes of all polyhedra with the same skeleton. The term generalized hyperbolic polyhedra I will explain a bit later. And Giulio Belletti, in 2021, in his work, he looked at the right side of this equation, and he proved that this supremum is equal to the volume of some specific polyhedron gamma over line, which he calls the rectification of a graph gamma. And I will explain what rectification means also a bit later. So firstly, a bit informally about generalized hyperbolic polyhedra. So what is generalized hyperbolic polyhedra? On the example, we have a tetrahedron, and generalized tetrahedron, it can be just normal tetrahedron in hyperbolic space with finite vertices or with ideal vertices, the vertices which lie on the absolute and hyperbolic space. There's some different dihedral angles. Or also we can have what is called hyperideal vertices or superideal vertices, the vertices which lie outside the absolute hyperbolic space. And in this case, we consider truncation. So this polyhedron in the right half of the screen is also, we consider it also as a generalized hyperbolic polyhedron. And the rectification line is a polyhedron. And so this polyhedron is equal to, volume of this polyhedron is equal to the supremum of volumes. And informally, it appears when we, as in this picture, we suppose that all vertices are superideal or hyperideal. And when we try to push them further away to make the volume larger, and to the point where each edge intersect the hyperbolic space only once. And then they consider truncation, and this the rectification appears. And formally, the rectification is an ideal right-angled polyhedron, and its graph is a medial graph of the graph gamma. The medial graph is the following. So suppose we have a graph G, and we create a new vertex for each edge of the graph G. So the vertex of the medial graph is the vertices correspond to the edges in the medial graph. And we connect two vertices by an edge in a new graph if and only if the corresponding edges, they lie in the same phase in the initial graph, and they go subsequently one after another. So in this example, we have a graph in the prism, and this is the medial graph. And another thing I want to notice about medial graphs is that medial graphs have two types of phases. The first type of phases is the phases which correspond to the phases in the initial graph. For example, this phase, this foreground corresponds to this foreground in the initial graph, and it has the same size as the initial as the phase in the initial graph. And there is another type of phases, for example, is this one. This phase corresponds to the vertex in the initial graph, and the size of this phase is equal to the balance of the vertex. First, an example, the simplest example is tetrahedra. So what I want to do here, so I want to use this latest result simply to get from here, get volume bounds here. So if we know that supremum of the volume of P is equal to volume of graph over a line, then the volume of P is less or equal to the volume of graph over a line. And so if we can calculate the volume of graph over a line, or can estimate from above the volume of graph over a line, then we can get some volume bounds. And first example is tetrahedron. In this picture, we see the graph of the tetrahedron and its medial graph, which is like drawn inside of it. And we can notice that this medial graph is the graph of an octahedron. And from this, we can conclude that the volume of a generalized tetrahedron is always less than the volume of right-handed, the volume of its rectification, which is right-handed ideal octahedron. And numerically, this volume is equal to 3.663, etc. So in this case, the rectification was simple. It was just an octahedron. But in general case, it can be not like that. And this theorem says that actually, for each ideal rectangular polyhedron, its one skeleton is a medial graph for some other polyhedral graph. So each ideal rectangular polyhedron is a rectification for some graph. And now I will talk about ideal rectangular polyhedron in general. Some slides in this section you will intersect with slides from Andrei Egorov's lecture, so we'll sometimes go faster. So the Andreev's theorem gives the recursion on the graphs of ideal rectangular polyhedra. This is actually a corollary of Andreev's theorem, which is more general. But so if we have a polyhedral graph, so free-connected planar graph, then it's realized it's a graph of ideal rectangular polyhedron, if and only if this graph is four-valent and it's cyclically cis-connected. Cyclically cis-connected, that means that if we want to divide graph into two parts, we should both containing a cycle, we should delete at least 6 edges. And this realization is unique. This table shows how many graphs for different number of vertices satisfies this theorem. For example, for number of vertices equal to 6, we have only one graph which satisfies this theorem, and so only one ideal rectangular polyhedron. And this is an octahedron. And when number of vertices is equal to 21, we have more than 72,000. The example can be antiprisms. So antiprisms, AN is when we take an n-gon on the top and gon on the bottom and connect them by triangles. This graph satisfies the Andreev's theorem, so it's realized as an ideal rectangular polyhedron. And for this antiprism, we have an exact volume formula. And another great thing about antiprisms is that all other ideal rectangular polyhedra can be obtained from antiprisms by applying just one move called H-twist. And H-twist is performed the following way. We have a polyhedron, as here on the left side. We choose some face in this polyhedron. We choose 2 edges in this face. This face should not be a triangle. And we do the following. We delete these 2 edges, create a new point, new vertex, and connect the ends of the deleted edges with this point. This is called an H-twist, and the new polyhedron has one more vertex than the initial one. And this theorem says that all other ideal rectangular polyhedron, so if we have a polyhedron which is ideal rectangular polyhedron, then it's either an antiprism or it can be obtained from an antiprism A4 by some finite sequence of H-twists. And this slide just demonstrates this theorem. Each circle corresponds to some ideal polyhedron, and its lines connected to circles. That means that the upper one is obtained from the lower one by an H-twist. And so if we start from polyhedron A4, here it is. If we continue, we can obtain all other ideal rectangular polyhedra, except other antiprisms, which are shown here on the left in color. And also thing to notice here that you might see that there is a vertical line which corresponds to volume. You might see that the H-twist always increases the volume in this case, but it's not proved here. And now about volume bounds. So the first volume bounds for ideal rectangular polyhedra were proved by Atkinson in 2009. He also proved the lower one, the lower volume bounds. But I will talk only about upper volume bounds. So he approximates the volume from above by using the number of its vertices of the polyhedron. So the volume of any ideal rectangular polyhedron is less than or equal to this number, which linearly depends on the number of vertices. And another thing about this volume bound is that it's symptotically sharp. And if you want to prove it and you want to stay in this form, we can't improve this coefficient. We can only improve the free term. And so what we did with Andrei Egorov in 2020, we improved this coefficient. And this theorem is true, this volume bound is true for all polyhedra except an octahedron. And then just later, me and colleagues will improve this volume bound again, but only when number of vertices is equal to 24. Okay, now I will talk a little bit about how to prove this volume bound, just ideas of how to prove it. The idea is to decompose the polyhedron into tetrahedra. The decomposition can be obtained the following way. We choose one of the vertices, this polyhedron, we fix it, we call it vertex V. Then we consider, for each face, we consider the orthogonal projection of this vertex V onto the sum of the faces. When we connect this projection with vertices, and also consider the projection of this vertex onto the edges. And we do this for all the faces. In this way, we can obtain the decomposition on the tetrahedra. And then we know now to get the volume bound, we need to just estimate the number. So we can volume of polyhedron is equal to sum of the volumes of tetrahedra. Now we need to estimate the volume, the sum of the volumes of tetrahedra. And we will notice that that if we choose the initial vertex V differently, that some polyhedra vanish, some not. And we prove that if number of vertices is larger than 24, we can choose the initial vertex the way that this volume bound is true. This is just the main idea. And by using this volume bounds for ideal rectangular polyhedra and combining it with Belletti's theorem, we simply just combine them. We obtain this volume bound for generalized hyperbolic polyhedra. So if we have gamma, so a connected plane graph with E edges, and P is a generalized hyperbolic polyhedron, this one skeleton gamma, then we can prove the following volume bounds. There is 3 points because we have this 3 theorem, and they are true not for all polyhedra. So for example, if P is not a tetrahedron, so the medial graph is not the graph of an octahedron, then we can write this volume bound. So and it's written in terms of number of edges because edges, the number of edges in the initial graph corresponds to number of vertices in the medial graph. If number of edges are larger than 24, we can write this one. And if P is a tetrahedron, we already know that the volume of P is less than the volume of an octahedron. And before I will go to examples, I want to also present another type of volume bounds. So we here in this volume bounds, we only use number of vertices or number of edges to approximate the volume. But some other volume bounds also can be, some other parameters to graph also can be used, and some of them convenient. So in this volume bound, we also use number P3, which is the number of triangles in the polyhedron. So if polyhedron has a lot of triangles, then this volume bound is going to be better than the previous ones. And this is convenient because if the initial graph has a lot of trivalent vertices, it's going to have a lot of triangles in the medial graph because trivalent vertices correspond to triangles in the medial graph. And from this, composing this theorem with Belletti's theorem, we obtain this volume bounds. For example, here we also, it's just composition with Belletti's theorem again. And here we also use number V3, which is the number of vertices of variance 3 in the initial graph, because these vertices will correspond to the triangles in the medial graph. And the case when then all of the vertices have valency free, we can rewrite this first volume bound to this one. And now examples, for example, hyperbolic prisms. So if we have hyperbolic prism Dn, so it means that size of the base is n. For example, here we see d5, polyhedron d5. Then there is a known volume bounds for these prisms, which are proved also by Atkinson, but with his different work, not as the same work in which he proved volume bounds for ideal rectangular polyhedra. And now we can try to use the volume bounds we proved for prisms. We can calculate the number of H's, which is equal to 3n. It is easy to calculate, and we obtain very similar volume bounds by using the first theorem. But the coefficient is better here. But we also can notice that for prisms, all vertices are equivalent. Then we can use another volume bound with triangles, and we obtain here we obtain another volume bound, which is even better than the previous one, because coefficient here is better, it's smaller. Here is 514, and in this case it's 549. But even more, we can notice that medial graph of an end prism corresponds to the graph of the union of two antiprisms. And so the volume of the prism is less than the double of volumes of antiprisms. And since we know the exact volume of antiprism, we can even improve volume bound again to this one. And the last example, it's about a little bit different topic about link complements. Here I will only use the volume bounds for ideal polyhedra, but not Belletti's theorem. So there is a theorem which was proved by Andrei Egorov and Dion Thurston, and they proved if they have if there is a hyperbolic link K and the projection diagram D with twist number TD, then the volume of the complement of the link K is less than this number, which linearly depends on the twist number. The twist number TD is just the number of twist regions. For example, here we have 2 twist regions for this diagram. And they proved it by the idea of the proof. They used they had a diagram of the initial link K, and they made the following projection to obtain from this diagram the diagram that they call this process is called augmentation. On the first step, for each twist region they added they encircled each twist region by the additional closed curve, as well as for each twist region, and they deleted all the crossings in a twist region except one or except two. It depends on if here it was not even number of crossings, and here it was even number of crossings. And this operation, when we go from K to G, the volume is always increasing, because they proved that because when we go from G to K, it corresponds to the de infinity, and the volume is decreasing. And the next so when we go from G to L, we just delete all the crossings for each twist region. We delete all of them, and it is proved by Colin Adams in some of his papers from 80s that this operation is again not changing the volume. So if we have a volume bound for L, we can write the volume bound for K. And how to write the volume bound from A? They just proved that this the complement of this link can be decomposed into two ideal rectangular polyhedra, and they estimated the volume. And so since we have this volume bounds which calculates the number of triangles, we can use them to improve this volume bound. Here's minus 1.4. So we improve this volume bound in the case when number of twist regions is greater than 8. So here we used the number of this theorem I was in the previous slide, which also takes into consideration the number of triangles. Okay, thank you very much.
Ну, пожалуйста, вопросы, комментарии.
Чем полезны верхние оценки?
Ну, так.
В жизни чем полезно?
Не, ну вот чем понятно, сколько материалов строения. Нет, там перестраиваешь узел.
Нет, это не вариант. Хочется увидеть его дома. Откуда такая интересная константа 1.4?
Там вот количество треугольников, которые исчезнут, если вы выберете правильно.
То есть это не выдвиженное значение.
Это ровно 1.4.
Там
Нет, вы смотрите, здесь 10 вылетает, просто выносится, то есть, а там было 14. Вот. Да, здесь какой-то просто 10. Вт, кстати, это константа, это объем. Да, да, да. Это просто 14, просто выносится.
Можно вопрос? Получается, в доказательстве вы оценивали объемы идеальных многогранников, да? Вот, и разрезая их на тетраэдр, да?
Это в доказательстве вот этой теоремы, да? Ну да.
У вас есть какая-то прям общая конструкция, как произвольно разрезать?
Ну да, вот она. Как раз.
Да. А там произвольное число внутренних вершин появляется или нет?
Вы можете оценить,
можно ли такое разделение сделать, что будут вершины возникать? Можно.
Внутренний, в смысле, здесь новые вершины разделяются. Одна на выбранные грани, и все остальные на выбранные. Здесь на самом деле разбиение такое, что ваши тетраэдры, которые возникают, они прямоугольные. Тетраэдр, вот, который возникает при разбиении, у него 3 угла пополам, и они еще бесконечными вершинами, то на самом деле объем определяется одним углом.
Это ортосхема.
Ортосхема, если вы вот, и получается. Да, конечно.
А вот с антипризм я просто немножко опоздал к началу, там какие-то из первых слайдов. Можно что-то?
Да.
Это n, это сам количество.
Это объем, размер вот этого вот основания.
В основном.
Размер основания. То есть вот это октаэдр, у него основание 3.
То есть зависит только вот по каким углам вы там прямые.
Здесь прямые, да, все. Ну, прямоугольные. Раздел прямоугольный, если написал. Да.
А вот вы там, значит, приводили оценки там в процессе, то есть это как гипотеза или я по-другому?
Процессе, это значит еще. Мы недавно начали их записывать.
То есть они еще не доказаны.
Доказано, но не опубликовано, где не выложено.
И не обнародованы, скажем.
Они доказаны, но просто не выложены.
У меня, может быть, даже в продолжении прошлого доклада про полиреды, когда вы говорили, это там вот или шестиугольники грани, она сам углы, там они, значит, прямоугольные реализуются, да, что-то там.
Но если полирены, то можно их рассматривать как, значит, уже не идеальные многогранники. Ну, идеально тоже можно. Можно, например, как с конечными вершинами многогранниками, с разными вариантами углов. Можно с прямыми. Действительно, с прямыми углами реализуются все полирены. Да.
То есть не обязательно идеально.
Не обязательно, могут быть и не идеальные. И могут быть разные. Но есть ограничения, которые с теоремой Андрея получаются. Но они разные, достаточно разные.
Поскольку полирены, у них все вершины трехвалентные, то если уж они прямоугольные, то они компактные.
Треугольники компактные. Всё.
Еще вопрос, пожалуйста. У меня просто замечание, не знаю, можно было акцентировать. Когда вы говорили про тетрадь и изменили объем тетраэдра, конечно, имелся в виду обобщен.
Да,
То есть тетраэдр, еще у которого можно было вершину отсекать.
да, конечно. То есть
Это как бы глобально был
да.
эффект обобщен.
Да, как раз generalized.
Ну, да.
Да, обобщен.
Ну,
Ну, тот же
это
результат, да,
эффект.
есть у Чуджима. Ну, другими методами получилось.
Антипризмы, они чем интересны?
Ну, в частности, например, ну, во-первых, мы знаем про них точную формулу для объема, да, через функцию Лобачевского. Ну и, например, еще тем, что из них получают все остальные вот эти операции. По-другому интересно. И эта операция, скорее всего, увеличивает объем каждый раз. Мы применяем, и объем всегда растет. Ну, скорее, это не доказано. Ну, и они, скорее всего, имеют минимальный объем, если смотреть как прямоугольный многогранник, если фиксируют количество вершин, то минимальный объем среди всех многогранников антипризм, скорее всего, на маленьких числах получается. То есть там может быть 70 тысяч многогранников, там маленький объем.
Среди идеальных.
Ну, среди идеальных прямоугольников. А снизу есть у Аткинсона как раз, но они... Да, есть у Аткинсона оценки тоже через число вершин, просто я их не писал, потому что но они в идеальном случае хорошие, а для других случаев там для близких компактных.
Еще вопрос, комментарии, замечания. Квантовый вариант. Будем думать. Давайте еще раз поговорим.